All right, great. I would say let's start. So, hello everyone. Welcome back to CS6 Practical System Skills. So, before the industry night starts, kind of the last chance to gain some more practical skills to impress all the recruiters out there. So, what did we do last lecture? Well, last week, as you might remember, was pretty heavy on content. We did a lot of bash scripting, a lot of interesting stuff, and also the homework had, I guess, some challenges, but I hope you all managed. So just a little overview, we spoke about exit codes or exit status codes or return codes, and it's all the same. The basic principle is that 0 basically means success and as failure, and kind of the odd thing about it is that kind of we can use that to compose a logic or conditional execution of commands based on other commands using like the double ampersand and double VBAR. And the odd thing was that kind of true was basically 0 and false 1. So just flipped what like usually the intuition is. Then we talked extensively about like tests and how to write them in order to have like Boolean conditions to later use them in if statements. And for that we have like kind of one option which was like the test command or the command which is just like square bracket. And then we saw that there were like some issues regarding like white space and like kind of the oddness that you have to kind of when you compare numbers use this weird short strings like minus GT form, for example, if you want to check that the number is greater than the other. We also spoke a little about like how to group commands by using like a subshell, which is just like the single parenthesis, and like how this kind of connects to like the $sign and then the subshell. And also how we could execute a bunch of commands in our current shell environment using like curly braces. And the last one was like a little about loops, arrays, and functions. And so in order to kind of check a little how much we remember, let's start with a short recap quiz. And so I would just like ask you to kind of spend 5 minutes trying to fix these codes and trying to like kind of debug what is wrong here. Yeah, you can collaborate. Like, it's in the classroom. Always collaboration is encouraged.
Yeah.
Yeah, exactly.
Fixed
Yes.
Or should be double brackets. Yeah. With double brackets, I don't think you need spaces in front of it because it's not like a command.
Yep. Wait, so what
Yeah, I think this. Actually, you probably do because
it doesn't matter.
Yeah.
Because I think I tried it.
Okay.
Unless with the indentation.
Yeah. Wait,
what is the last one supposed to do? Like, is it supposed to, given two inputs, give the sum of the squares?
Yes.
Okay.
I don't know.
So just everyone, the last one is just like it should basically print the sum of the squares.
With the thing in front or without, or just the sum? Like, should it just give a number?
No, it should be like a string, right? I mean, it's
like
like
the string. It's like the thing.
Yeah, exactly. Yeah.
Wait, if you just enter like x squared, does it return x squared in like terminal without the echo or anything?
Well, that's the question, right? You know what's happening. When whoever has the notebook, you can also just try it out. But yeah, it's more about like kind of a little getting into this weird syntax logic that Bash usually has, because a couple of things are like different than usual programming languages.
I don't think you can mess the backticks inside.
Oh, you can?
You can.
That's not a problem.
Okay.
Oops. Okay, there we are back again.
Yeah.
Yeah, let's give it maybe like 2 more minutes, and then we can kind of check out what errors we found.
Is this one of the languages where you have to just modify it? You can't use whatever.
I don't know.
It might be. Because there's some languages where that just basically, like, bitwise, it could be.
Also, I don't know. I tried to find out the difference between.
And also it's in the second language. Values. Like it needs to bracket. This thing.
You just try to like set x equal to like 2.
Yes, and this is
Y equal to 3. And then tracking x caret.
Yeah, so let's make like 1 more minute, and then let's go over it. Alrighty, good. So let's see what we got. Any ideas on the first one? So all of them are wrong. So what is probably wrong in the first one? Yeah.
Double brackets.
Yes. Why? Like what's currently happening there?
Bash is just the spaces are also messing up the Bash's interpretation. Oh,
Yeah.
like
They are.
multiplication occurring.
So I mean, you definitely have the right idea. So basically, I mean, just in your words, what is like kind of the command intending to do, but what is it actually doing?
So it's essentially defining a variable.
Yeah.
By defining it x times 3.
Exactly. So, but what actually happens is like, so we know that like the dollar and the single parentheses are command substitution. That means we basically would try to execute here a command called x and give it the parameters star and 3. And as you said, the correct fix is like kind of just using double parentheses, which would do like arithmetic expansion, and so evaluate that correctly. Awesome. All right, the next one.
Is
Yes.
it possible to use just double parentheses and have some expression inside of it without assigning it to z? Because when I tried that when I was practicing,
Yes.
it never worked.
Yeah, exactly. What would happen in that case? Like, what was the issue? Do you
It
remember?
tells me command's not found. If I do like $sign double open parentheses 1 plus 2 and double close parentheses, it gives me command not found.
Exactly, because basically what it does is like you get like the string, right? And then it evaluates the dollar and so on, performs substitution. So it substitutes that string, then a new string happens, and then Bash tries to evaluate that string. So if, for example, this whole thing would be like x times 3, right? And let's say x is 3, then the resulting string would be 9, and it would try to execute a command called 9. But I mean, you can also use that behavior. I mean, I gave like kind of this example in the last lecture, which was like when you have like, for example, Python, right? And you have like 2 versions. You have like Python 2 and you have Python 3. And so what you can do is you can write something like Python, of course correctly written, and then you put in like here the whole thing, and then you can do like 1 plus 1 that equals 2, right? And then Python 2 is started. So that's like kind of the trick. So basically the string gets added, right, and then the command Python 2 will be evaluated. And so you can use that to kind of create that.
String again? Like, would you explain what you mean by string here again?
So by string I mean like basically, so this here, right, this gets substituted to be Python 2, just as one string, and then this is like used as a command, which is then run by bash.
Right. So you were explaining how that fits into the idea of double parentheses and $sign?
Yes, exactly, because what you do is basically you have just like here the part dollar and parentheses, right? So this evaluates to 2. And then this becomes kind of part of the whole string that you submit on the command line interface. And then the command line interface evaluates that command. So which means you're back in like kind of the read, evaluate, print loop, right? So basically the whole evaluation happens before the read step starts for bash. Like the whole command substitution and so on.
So if you have z equals that, then it will understand that as a command to set z equal to it?
Well, if you have something like, so let's exit this. If I have something like this, c equals 1 plus 1, right? So, I mean, we would expect this is like c equals 2, and that's exactly what happens, because this is nothing else than if we would write just c equals 2. So basically, the dollar and like the double parentheses just substitute the whole expression and it becomes 2. So that's how it works.
It's just turning into a string that's then read.
Exactly, and that is how it always works. It's just always kind of string substitution in like some fancy way.
Okay.
All right, let's go for the second one.
Wait,
Alright.
why doesn't it work if you drop the $sign?
Okay, so you mean if I just do like something like this?
Yeah, if z is equal to, and you drop the $sign.
Okay, yeah. Any ideas why this doesn't work? Yeah.
I mean, like, it doesn't return the value inside that's evaluated inside the double parentheses. It like probably returns something else.
So it doesn't return anything. That's kind of how the just double parentheses are defined. So this here will of course first raise like a syntax error because I mean, it doesn't make sense, right? You can't read that. But like if you just do like 1 plus 1, right, this, right? You don't get any output back, but you get like kind of the exit status back. So this is like kind of where you use this syntax without a dollar for like assignments or equals or operators like Boolean operators and stuff like that, which we talk extensively about like in one of the lectures. Yeah, another question.
Can you not store like an exit code inside a variable?
Okay, again, so what do you want to do? You want to store the exit code in a variable?
Yeah.
Okay, yeah, you can do that. So you know, like kind of that dollar question mark is the exit status of the last run command, right? So I can just do like x equals like this, and then if I echo the x out, I get like the result. Because like dollar question mark is again just substituting this part as like my last exit status of the last run command.
And why doesn't that work if you just said x equals double parentheses 1 plus 1?
So if I do x equals double parentheses,
Is
and
it
then
because the exit code happens after you like run it? Like it returns that after you run
okay, so if I do like this here, right?
Yeah.
So this will give me first a syntax error, right? But like if I would run it like separately, then theoretically this should give me the syntax error. Because if I have a syntax error, this will be also a wrong status code. But I mean, here it just basically fails already just reading the tokens or like doing the tokenization step because it's just invalid syntax. Great, let's move on to the second one. Any ideas what's wrong here? Yes.
If you're gonna use single brackets, you should use the flag. So -GT LE greater than or less than.
That's
And then,
correct.
Since this is an if statement, you have to close it off with a 5.
Yes, that's also correct. One more arrow is in there.
Also, don't you have to separate the or
Yes, exactly. Because that's like exactly where kind of the bash extension comes in. So you could either use like kind of the double square brackets or separate it in this syntax of like always like kind of combining the exit codes of the individual tests. Yeah.
Can't you also just fix this by doing double brackets?
We can, yes. Okay.
Do you need money signs in front of the X's?
Yes, you need those two. Exactly. Perfect. Yeah, I think then we got it. And like, yeah, you have to close with a phi, and you have to also put in like the semicolon, and that's it. But there's like multiple ways to fix that. But like, I mean, we kind of talked about all the errors I artificially put in here. All right, let's go for the last one. Okay, one more question here.
If you did the double brackets, would you need the dollar sign?
Yes.
Why do you need them for the brackets but not the parentheses? The money sign in front of the variables.
Yeah, that's like kind of one of the oddnesses of like
That's
bash. Yeah,
okay.
that like kind of when you have like kind of this arithmetic expression, it basically just reads the variables without a dollar sign, which is a little weird, but that's what it does basically. One more
I
question
just
here.
have a question about the semicolons.
Yes.
So, couldn't you also use the relevant quotation marks to do this, or why? Like
Quotation marks where?
like the use of the semicolons in this case.
Yes. Okay, so why do we need the semicolons? So the idea is basically that the syntax of the if command is like multiple commands, and we separate them by using the semicolons. And so I just wrote on one line, that's why we need it. However, we could also just always do like a line break instead of the semicolons here. So that's just a kind of the syntax to put everything in one line.
So there's no other way to put it in one line.
I'm not sure. Maybe there is, because Bash usually has a lot of weird tricks that you could use, but I mean, you definitely have to use the semicolon like after the test command, and then you have like kind of then comes another command, and that has to be like kind of also done with a semicolon before the else block starts. So I would say you need it. However, there might be some weird way in Bash how you could hack together a different solution.
Is
Okay.
it also missing like the FI?
Yes, like mentioned before, yes, it's also missing that one. Yeah, that's completely correct. Okay, cool. Let's move to the last one. Any ideas what's wrong here? Yeah.
So the symbol that we assume to be exponential is actually not exponential. So it's not the right operator in this case
Yeah.
to use.
Very good observation. Because what's actually the caret operator? What's that doing?
Supposedly it's bitwise store.
Exactly. So that's like kind of the first trick to remember, because it's like kind of C-like operators. And what's the second issue? Yeah. Because what would happen again in this case?
Well, it would just interpret the thing that's supposed to be read as a command.
Exactly. So I would say like, right, again, it's like run command X, give it like the caret symbol, 2, plus, and so on as parameters, and the whole thing. Cool. All right, so let's resolve this. So, I mean, you guys already got it. Yeah, you basically have to fix the first one by using arithmetic expressions, right? The second one you can use like tests. You can also use the double brackets, like that's really your choice. And for the last one, you basically have to know that the exponentiation or power operator is like just like a double star, like more similar to Python than like to other languages. Great. All right, so let's move on to today's topic, which is SSH, or Secure Shell. In order to understand what SSH is doing, why we need it, how to use it, and what the cool things about it are, we have to dive a little into basic networking. I'm not going to talk about like in-depth networking, because there are like full-fledged classes for that, which I highly recommend to kind of take in some semester if you're interested in computer science. However, we are just going to talk about the essential basics you need in order to understand what's SSH doing. All right, so let's see how usually networking works. So we have basically two machines. We have Tux machine and cs.brown.edu, and they take up like two different roles, which is like usually one is the client and one is the server, and the client asks the server to do something. The server responds with like an answer or just a response, and then this kind of continues. And we basically name these machines by giving them each a host name. So we also just call these machines basically hosts, and they can be like anything. They can be like an actual device or like some virtualized device, like a virtual machine or something like that.
Why are they called hosts? What are they hosting? Your program?
Yeah, or service. I mean, it can be really abstract in that matter. It can be also just some service that you're reaching under this name. So that's like the host of the service, like for example, a database or a chat application or whatever, a banking application. It can be really anything. So that's why it's kind of very general. But I mean, of course, the actual code has to execute on some physical device in the end. But it could be also a fridge in the end, right? All right, so in order to connect to a server, we kind of need to know where it is. And so we assign it an address, or somebody else assigns it an address. And so in the network, that's usually done using an IP address. And there are like two flavors. We have like version 4 and version 6. I'm sure you at some point came across this already. Basically, one is just like 32-bit integers. The other one is 128-bit integers. We can divide them into segments. There's a lot of like information on how to do this, how to do like subnets and so on, which is all like kind of the topic of a network class. For us, it's just a simple address which we use to reach a host. And so basically, I already said like we give each machine, device, service, whatever, a host name and call it a host. And so we actually also have like kind of a cool command because we're working in a Unix-like environment. And so if we run something just like hostname, we get the host name of our own machine, which in this case here is just like my MacBook Pro. And because I'm currently on the Brown network, it's like named according to some like Brown rewrite rule. All right, so one host communicates with another host over a connection. And so this connection kind of needs like two endpoints, right? Like one host has one outlet and the other one has another outlet. And so just in terms, we call each of those outlets sockets. And so on a Unix-like machine, there are in general 2 to the 16th sockets available, which we identify by a 16-bit on-site integer. And also each of these sockets binds to a unique port number. So that's why usually the socket is identified by its port number, which is also a 16-bit on-site integer. And so we basically have like sockets/ports from 0 to like this number, which is just like 2 to the 16 minus 1.
If each socket needs its own port, there are far fewer ports in that number than there are 2 to the 16 sockets. Isn't 2 to the 16 like in the billions? Trillions?
Wait, no, I don't think so. So 2 to the 10 is 1024. And so a couple iterations after that, and I think you should land at this number. All right, the special case is that like port numbers smaller than 1024 or 2 to the 10 are reserved ports. So if you write your application, you should not use those ports unless you really know what you're doing. So how does it work? Well, we have usually the server, then it has like some port or like all the other ports, and it listens on this port. Then a client comes along with the same port, makes a connection request over that port to the server, and then they establish a connection, and they have then like kind of a two-way communication link between those two machines. Yes?
Oh, so the ports on the server and the client have to be the same?
Yes, because they kind of uniquely identify the communication link between the two of them.
What exactly is like a port? Like
a port?
Yeah, like what? Like,
okay,
what
so a port is just a number in the end.
Okay.
And so how it works is like when you have internally, like you have your kernel, which is communicating with the OS and so on, and there's a network card, right? Then it basically is an abstraction if messages are received over the network where to put in which basically inbox the message. And like there are basically the 2 to the 16th different inboxes, which are the ports. And so that's where like kind of the messages are stored together with the address. So it's really just like a port. There's actually also in Bash the option to kind of read directly from these ports, but we're not gonna touch it because the reason for that is like it's a little more esoteric, and like they're just like way better tools to work with like sockets than just using plain bash, in my opinion. All right. Yes. So as asked a second ago, in order to specify the connection, we need kind of three things. We need 2 IP addresses and 1 port, and then we kind of have the connection uniquely identified. So, yeah.
So everyone, like in the world, is using these ports.
Yeah.
And they're clearly not, they're like to the 16th amount of ports. And it's just okay if they're like multiple views on the same port as long as like
Yes.
2 IP addresses.
Absolutely, yes.
Okay.
Because you basically send them, and then kind of the IP address is where it is directed, and the port is kind of which channel you're subscribing to. However, I mean, the actual networking is a lot more complicated, and I'm just referring here to like the networks class. That is like you have not only like kind of direct connection to everyone in the world, but rather you go over like switches, hubs, routers, and so on, and they all kind of mess around with your connection, right? Like some of them, for example, filter out certain ports, or some of them translate ports to other ports, or others kind of reroute your address and like switch out your address or packaging. So they do all kinds of tricks to kind of go around the limited number of ports, and like also like the issues that there is not a direct communication link to everyone. And I mean, you also don't want that for security reasons often. Yeah.
Wait, so can you connect like your client and like a bunch of servers, like the 65,000 minus the 1,024? Like theoretically, we'd be able to like connect to all of those servers.
I mean, you could. There is also like kind of there are often like some limits, right? And that's like, for example, if you run a website or so, right? And you want to have like a real-time chat application, you basically have for each kind of machine that you want to directly connect, you can open a socket. And the web browsers actually have a built-in limit for the number of sockets you can open. So at some point it usually gets throttled because just the throughput gets like very low. But theoretically you could, yes. But like, I mean, in the other sense, it's like, do you really want to describe to all the network traffic that's happening? I mean, there's a couple companies like Google or so which love to do that, but like, yeah, your personal machine might be very soon exhausted. All right. Speaking of that, so as I said, networking is a topic on its own. It's very interesting, so highly recommend to go to a class. And how it kind of works is that there is like some abstract model that was established to describe the different layers across over which communication happens, which is called the Open Systems Interconnection Model, or OSI model. And so how this works is basically it breaks down the different connection steps in multiple layers, starting like from the physical layer where you just send like basically bits and bytes, to the data link where you kind of find the devices over like a physical link, to like networking where you have like packets, addressing using IPs and so on. And then you kind of go one step further where you have like all the host layers, which are like more than software logic in terms of like how do you segment a message into multiple packages, how do you stitch them together, how many packages should you send, and so on. And then we kind of slowly approach more the layers we care in CS6 about, which is like kind of the application and presentation layer. Though like here we really have like just the focus on the application layer, which means like what kind of logic are programs doing when they communicate over the network. All right.
Considering that the OSI is just the hypothetical, it's not actually used, why are we talking about that?
I mean, it is sort of, it started out as an abstract model, but I mean, if you look at the concrete implementations, I mean, many implementations sort of try to stick to it, not all of them, which might be like due to like, I mean, sometimes you just want to have your solution a little bit more efficient, right? Or sometimes just too much overhead there. But still, it kind of helps you to understand what kind of layers are working, and often like, when you write your own software, you want to really reuse layers in software that other people were using. So it kind of helps to understand where an application is or where technology is in the whole stack over the network. That's why I kind of mentioned it here. And also like if someone took like a network class already, we're still talking about the same thing in the end. All right. So when we talk about like IPs, there are like multiple problems. One is they're quite limited. The other is they're hard to remember, and also their assignment frequently changes because the pool of IPs is limited. That's also why we have like this whole thing of like transitioning from IP version 4 to IP version 6, which I think is now going on for 15 years or so and still not done. So in order to make our life easier, we basically want to name our machines in some way. And so there are like basically two options. One is like we just can assign it a host name, which is just like some name we pick assigned to a computer, and then we can just identify this computer, or better, just like get its IP address based on the host name we had just assigned it. The option is we can use some service that somebody else is running, or we just created the service, or we started it, and there we just supply like also some name, usually like a domain name or so, which you can use to also translate it into an IP address. So let's see how this works. So the easiest is like kind of just defining our own host name. And how we can do this is basically we can just edit a file on our computer. However, you need root access, so this is mostly when you're now working on your own machine. You can't edit that on the department machines. And that's like stored in /etc/hosts. And so what you do is basically just type the IP address and then give it like a host name. And so one of the kind of famous host names that you usually frequently encounter when you read through like how to set up a web server and so on is like localhost. And so localhost in the end is nothing else than a tag to tag like the special IP 127.0.0.1. And the lookup for this is stored especially like in this file here. And so just to give you like kind of an example how this works is I kind of did this here on my machine, just making it a little larger. I think that's better to read. So I can basically just like print out my hosts file, right? And here we see like I have like kind of localhost, broadcast host, and again localhost. I have some Docker stuff going on. And here I just added an entry for the machine that I'm usually using to like demonstrate a couple commands, which I just called here CS6 server. And the cool thing is, so if I want to, example, to just like ping the server by using the ping command, I can then just write CS6 server, and then, okay, I get a request timeout. Do I have internet? Yes. Or I can use like SSH to kind of log in. And then this is just like a shortcut, and I don't have to write the IP or like a complicated URL. And you can basically assign whatever host name you want here, and this file usually precedes the other files. So this is like kind of a cool utility to just like quickly identify some host somewhere on the internet. Yeah.
Kind of like a side question. What are packets exactly? Because are they just data that transfers through like the connection, or what are they essentially in this entire role?
Okay, so a packet. So let's start like at the lowest level, it's kind of just bits and bytes, right? Then, however, the problem is that when we transfer all these bits and bytes, some of them might get lost just for like physical problems, right? There might be collisions when we send packages at the same time over the same channel. There might be data errors, like something physically goes wrong and so on. And so we usually put them together in like batches, and then we want to reassemble our message from these batches, right? So this is like kind of the lowest level. Then we kind of go one step further, and it's like we define a logical message that we want to send, like just bits and bytes. However, we might have a very large message. Let's say you want to send a 1 gigabyte file over the network. So would you send a 1 gigabyte file over the network continuously? Might be a bad idea, because at some point your connection might drop, it might crash or whatever, or also like some of the hosts or like connections are just not anymore existing over the time because just someone plugged out like a cable or so, right? So you want to reroute it over the internet and so on. So for this reason, it kind of made sense to kind of divide your message into packages, and the packages themselves get again divided into fragments and so on, and then in the end everything gets stitched back together That's typically what your network card does. However, as I said, like typically all the details on that are like in a network class, and that's also like kind of part of how to do that and how this works together. Another question here.
Is it that IP addresses can be identified by the slide before this? That they can be identified with a special host name or with a
domain name?
Domain name. Yeah. Are you going to explain what it means by domain name?
Yes, I'm going to explain in a second. All right, so the second option, so we saw we could just like define a host name, which is just one tag that we specified for this IP address, is kind of have the problem that IP addresses might change and also like they get translated and so on. And for that reason, it's often easier to kind of have some servers which deals with all this like dynamics in the network to give us the current IP which we can connect to. And so the way this works is we need to kind of locate the resource which we want to identify. And there is like kind of one way that's at this point like kind of standard to identify a resource over the network. And that works by using a so-called uniform resource identifier. And so the generic syntax for this works like this. We have like kind of first a scheme, then we have like a column. Then we have optionally an authority that we can give it, a path, an optional query, and a fragment number. And the authority itself splits up into like user information and host and like a port. And so the thing to kind of keep in notice here is like that the path has to start with like a slash, but it's considered part of the path. That's why it's kind of not like explicitly mentioned here. And so this looks like kind of first a little complicated, and you know, okay, URIs, what's that? Well, luckily, you kind of saw these all on a daily basis because URLs are like one special form of URIs which are used to basically identify, for example, a web page or anything else. And the trick is that basically your URL, which is like short for like Uniform Resource Locator, just points to some resource. That can be like a text document, an image, and so on. And it also like just follows this URI pattern, right? And so when we speak of like domain names, basically this is like sort of a domain name because we defined like one domain for which this is valid, right? Which is here basically web resources, web addresses. And then we can ask some servers to kind of retrieve the concrete IP address and then also like what else to do like under this IP address using like a URI or like URL. And like kind of the domain system for that is DNS, which is called Domain Name System, or just basically took over this name. And this is basically when we talk about URLs, we can split it up in like the different parts of a URL, like top level domain and so on. And then we have like specific servers which have like the lookup for like a URI that we give it and translates that back to an IP address of the server where the content is stored at this point. And the thing is that this is like really all dynamic. So that means, for example, if you look up a domain name through the system, you might end up with like different servers, which can be also used to like load balance. If you want to do something like that, if you run like, for example, Facebook and you have a lot of requests for like www.facebook.com. So let's see how this whole lookup works. Luckily, under Unix, we always have a tool that does the job for us. And so here the tool we can use to look up host names and translate them to IPs is get and then hosts, and then we just give it like either a URL or a host name. And that gives us a list how we can look it up. Under Mac, there's a slightly different command. And this is also not the only command. There's like multiples which you can use, but that's just like one very convenient to use one. And so how this works is basically, if I, again, go into machine, I think now I have to actually log into the remote machine. Okay, so I can do something like get and hosts, and let's say unix.stackexchange.com. This basically will give me a list of IP addresses which kind of the DNS service provides for me to have like the lookup from like the domain name to like the actual IP address. Works also like for other hosts, like for example, I can look up what the host for cs.brown.edu is, which is in this case just one IP, so no load balancing here. I can also check out what the IP address is for the SSH service. We see it's a different IP address than like the main website. And so this is like kind of the way how we actually find where to send packages or where to connect to. Question here.
When I type in hosting on my computer, it's like my name something and then like cs.brown or brown dot something, and that's because we're connected to the brown Wi-Fi.
Okay, I'm not sure if I follow. So
Like,
can you give me an example? So if I have...
If I, like, you showed us a command earlier to, like, just type in hostname, it prints out, like, the hostname of your own device. And I get, like, shalom something dot devices dot brown dot edu.
Yeah.
And that's because I'm connected to the brown
Exactly,
Wi-Fi,
yes.
And that's my current hostname.
Yes. And so if your settings for sharing are on or the network is configured like that, for example, I could just type that name here and I could look up your IP address. So that would work, yes. Because maybe I want to connect to your computer, right?
But that's the IP address only for, like, this hostname, the brown.
Yes, exactly. That's like currently. And so kind of, I mean, as said, I want to go deep into networking, but like there's basically like subnets. So we are all here on like one subnet right now. So we can have like a couple IP addresses. Then there's like kind of public IP addresses, which you can like share and everybody can connect to. And then there's like private IP addresses, which can't be accessed from the outside. And so there's like kind of multiple layers. But yes, if you're connected, you have an IP address. And like really every device has an IP address, like smart fridges, smartphones, watches, what else? Maybe someday even Coca-Cola bottles. I mean, somebody has just found a startup for that. And yeah, so basically everything has an IP. And you can connect it and look up the host name if there is one given to that device. All right, so this brings us to the important topic. How can we actually access a remote machine? And so to answer that, let's have first some history of commands that we should not use. So as part of like the Berkeley software distribution, I mean, already then, like users kind of found it very interesting to remotely work on machines and log in, execute commands there, and so on. And so there were a couple programs which are called like rlogin, rsh, rexec, and there's a couple more. Basically always like for remote login, remote shell, and so on. And they basically allow to log in into these computers, but they have a couple issues. And so basically the problem is that all these tools send your password without any encryption. So somebody just has to basically sit next to you, can read the password via, for example, Wireshark, which is a tool to just like sniff on a network, and then he or she can log in to your remote machine. Hence, you should not use them because they have an inherent security risk. And there's also like one command which is the absolute worst, and that's like rlogin. Because in order to log in to like a remote machine, how this works is it basically checks, oh, okay, are you logging in from an IP address that I know and trust? And then if this is the case, then you can basically just work on a remote machine because you're granted access, just because you have the right IP address. However, it's very easy to fake an IP address. So you could just sit down, say like, oh, okay, now I'm like 192.168 and then something else. And you just know by chance that this is like one that works, and then you have like access to the whole remote machine. And you can also like just iterate over all of that. And I mean, a computer does it very quickly. So basically, if you ever find a computer with rlogin, it's not safe at all. Hence, the big question is, how can we encrypt data, passwords, usernames to securely work with a remote machine? And so, starting with that, I'm going to talk a little about cryptography. And we start out by the basics, which is like symmetric encryption. So what's the basic idea of like symmetric encryption? Well, the idea is you have one key, you have some plain text, you encode it, you get a ciphertext, and then you use the same key to decrypt the text and get the plain text back. And so you could think of, hey, that's a pretty cool idea. I could just like encrypt all of these things, then I log in and so on, and it just works, and everything is good. However, that unfortunately doesn't work really well. However, nevertheless, it's still used, and it has its use case. And so how is it used today? Well, there's a couple of like kind of standard symmetric encryption algorithms. Just a couple listed here, like Blowfish, AES, RC4, and all the other RCs and DS. And so one of the widely used ones is AES here, which can be used with like 3 different key sizes. And so the general idea about like symmetric encryption keys and key sizes is the more bits you give the key, the better the encryption is. However, the slower like usually encryption and decryption becomes. And the cool thing is we can actually encrypt our files using symmetric encryption by just like specifying a password and then encrypting, decrypting it. And the tool of choice we can use for that is OpenSSL. So how does that work? Well, if let's say we want to just encrypt, decrypt a file with like some password, which just we know, we can do so by running like this command. So here I basically start the command, we give it like what type of algorithm we want to use, -e for encryption, then -pass, there we specify the password, which is here secret, and then we just give it like an input file and an output file, and then we have already encrypted our file. So we can like just do this like as an example here. So I'm working like here on my machine, right? And so what I can do is can start a file like whatever message.txt, and then something like Tux loves seafood or so, right? Then I can just like quickly do like a hex dump of that. As see here, I can kind of read the clear text, right? So because the command is so long, I also printed it out. So let's see how this goes. So here, basically now what I can do is can type like OpenSSL, then IS 128 CBC -e, then I give it the password, pass, and then whatever secret or so. Then I do like the input file, which is just the message, call it out encrypted.txt. Let's hope it works. Yep, it works. So if I do now a hex dump of my file, I basically see that the whole thing is encrypted. Can't see anything there. So this is like one way how you can safely encrypt your files quickly. And so in order to decrypt the whole thing, I kind of just run the same command. Of course, a little different. So I use like decrypted here now. As input, I give it like the encrypted file. Again, put like the password secret, and then D for decryption. So if I do this, then again I can just hex dump it quickly, and I have like here my message decrypted. So that's like one handy tool you can just use to kind of encrypt your files on department trees or whatever. There's also a lot of more options how you can use OpenSSL, but I kind of just want to mention it because don't try something like, manually encrypting data. Just use a tool like OpenSSL, which does the job for you, and quickly encrypt your private data if you need to. And of course, remember the password, because there's no chance to easily recover it unless you have a very, very good government contract. That brings us to one more problem. So now we know kind of how to encrypt, decrypt files quickly. However, how can we actually exchange the key? That's actually a big problem that was like long unsolved till the 1970s roughly. And previously it was usually you just exchange it like using a codebook or some other kind of safe channel, like a person that just like knows the password, gives it to you, and then immediately forgets it in the best case. And so the big idea that was kind of done in the 70s or investigated how to do this is asymmetric or /public key cryptography, and that's like kind of the same. And so here the idea is that you basically generate two keys, one public key and one private key. You only share the public key and use that to encrypt the message. But you can only decrypt this message using the private key. And so the private key, as the name implies, you basically keep private and never share out to the public. So also general usage for that. So we have kind of here two famous cryptography persons, Alice and Bob. Then we have the public. So Alice kind of generates a private key and a public key. Then she can use that to encrypt. Then Bob wants to send Alice a message, so he has some plain text. He uses Alice's public key to encrypt it. The public can't decrypt it because decryption only works with the private key. However, Alice can decrypt it because she has the private key corresponding to the public key. Then, based on that kind of idea, the same people who investigated, which are like Diffie, Hellman, and Merkle, designed a sort of safe key exchange protocol, which is the famously called the Diffie-Hellman-Merkle key exchange protocol. And so how it works, it's basically we have also private and public keys, and here it's just illustrated like using colors. And with that, what we can do is basically we first like each generate a private key, then we have a common secret. We combine the private keys with the common to have like some public secret, and then again we can kind of use these public secrets to combine them again with our private keys, so we have a shared private secret key. And with that, we kind of created a shared secret key which you can use for like symmetric encryption from then onwards. Yeah, there was a question over here.
Yeah. I was just wondering, why do you need a public key?
Well, so okay, so you basically want to send a message from one person to the other, right? So if you use one key that you previously agreed on, you basically do symmetric encryption, right? You send the message for this key, and then you decrypt it using the same key. However, how do you transport the actual key? And if there's someone in the middle, he could just like read the key, and then he has the key and could encrypt your messages, right? So that's not safe. Therefore, you want to have some procedure how to safely exchange the key.
So the private key is transported by the public key, in essence.
Well, no, so the question is how to do that, actually, right? And so kind of the historic versions of that is like you have some book where keys are stored. And that's like how it was done till the 70s. However, that's unsafe because just one person has to grab the book and then has all the keys and can use them to decrypt all the messages. So that's rather unsafe. However, like kind of the exchange mechanism here, you don't have any book, but rather you have like a public key, but the public key is on its own useless because you need the private key to decrypt the message. So this is kind of one way how you can exchange a key. There are like multiple ones, but that's a kind of the famous standard key exchange till today still. Right, so this kind of works, and as I said, there's a lot of mathematics involved, usually based on discrete structures. And so if you want to know more about this, there's also a class for that, which is usually the cryptography class. I think it runs like CS151. And so this all sounds like a cool idea. However, there's like one problem. And that is like you can do a man-in-the-middle attack, which means you basically take all this public information, position yourself in the middle, and then can kind of fake for each of Alice and Bob the shared secret, and you know only the true secret, and you can use that to basically decrypt everything. Hence, the problem of this whole exchange idea is that there is no way yet to authenticate whether Alice is the true Alice and not like a fake one, which here kind of Eve takes the position for, and Bob is the real Bob. So you basically also need authentication of the two communicating parties. So that's kind of the problem. However, there's like kind of another solution, which is called RSA key exchange. And so RSA is another famous cryptography system, besides the Diffie-Hellman one, based again on like a couple of people from the 70s, like Rivers, Shamir, and Adelman from MIT. And here the idea is basically we not use like kind of this procedure to generate a common shared secret, but rather we just generate two key pairs again a private and public key, and then we can use them to kind of pass messages to each other by basically encrypting once like with a public key, right? Then with the other public key, and then we decrypt it like with the private keys. It sounds very similar to like Diffie-Hellman, however, there's a lot of differences kind of in the underlying math, and so they are basically two just different principles how you can perform key exchange. And again, all the details for that are usually lectured in a cryptography class. So yeah, as I said, basically both can be used to just exchange a key or perform direct encryption of the messages. But they have like kind of different underlying principles and are vulnerable to different attacks. And there's also like kind of always this general notion that whatever technology you use, there's always a trade-off between like speed and applicability. And so symmetric cryptography is usually faster than asymmetric cryptography, but asymmetric cryptography can be safer than like symmetric cryptography. Hence, what you usually do is like you exchange the key using like some asymmetric algorithm, bless you, and symmetric cryptography to then encode the data. All right, so why do we care about this? Well, for CS6, we just need to know it exists out there in the universe. It has like each some shortcomings, meaning we want to configure it to our needs. And our summary is we basically generate a key pair. We only share the public key and never, never, ever share the private key. And that's like really, really the big message I hope you all take out of this class today, that you should not share your private keys, because that's what like many people actually love to do. They just send their private keys over emails, give them to system administrators happily in desperate kind of hope that they solve their problems. However, this class will enable you to not do all of this, but rather understand how you can just do it on your own. So before going on, what I also want to mention is that kind of, so we just share the public key and we never share the private key. But if we store our keys on a system, we still have the problem that we have to save somewhere our private key. And so in order to kind of protect our private key, we usually use a passphrase, which is just another password. So basically symmetrically encode the private key again using some password that we remember, which can be something easy. And that is just if someone gains access to our system, the private key is still somehow encrypted and not just lying around in its plain form. So that's basically what a passphrase is for. Yeah.
Where is the private key stored?
We will talk about that in a second. All right. And that is like, so far it was all like very theoretical, so let's do it practical now. And that is like using SSH, which is basically our practical implementation of public key cryptography. So yeah, SSH stands for Secure Shell, was invented in Helsinki, and it is a cryptographic network protocol to allow to safely log into like some remote computer, work there, execute commands, and so on. And it is today the de facto way of like working with machines over a network. So how does it work? Well, it tells pretty much all of it for us. It sets up a safe connection, logs in, authenticates users, and so on. And at the end, what it allows us to do is we can log in securely remotely, and we can also like transfer data, for example, if you want to copy files and so on. So there are basically two programs that enable us to do that. We have a client program, that's like what you usually type in your computer, SSH, and there is a server program which kind of handles all the requests that are coming in from the client programs, which is SSHD. And so the thing is, if SSHD as a program is not running, you can actually not log into a system. Hence, you should always make sure if you have a server somewhere started up that you don't kill the SSHD process, because worst case, someone has to go in the data center and restart the computer again for you and kind of connect the keyboard to restart the service. And there are a couple of different implementations because SSH is just a protocol, and the most popular one is OpenSSH. So SSH itself provides kind of 4 different authentication methods. You can either use a password, you can use a public-private key pair, then there are like 2 more, which is like host-based and Kerberos. However, the one you want to use is basically public-private key pair authentication. So let's talk a little about the different authentications. So first one, as I mentioned, is password authentication. That's the one you use when you log into department machines. I also checked this morning. Unfortunately, key pair authentication seems to be disabled at the moment for whatever reason. So basically, you just always have to use a password if you log into like department machines. However, the cooler thing is using key pairs. And so how this works is basically you first generate keys using the SSH keygen tool. Then you copy the public key to the remote machine and append it to the special file, which is stored in your home directory, then in the secret folder SSH and authorized keys. And then you can basically log into the remote machine by using the SSH command and just like giving it a private key. So how does it work under the hood? Well, you first generate a key pair using this program. And there's a kind of 2 locations where these keys are usually stored per default. And that's like when you use RSA to generate your key, so you can select basically what type of algorithm to use for SSH, and RSA is not the worst choice. And then you can store it in like ID_RSA and ID_RSA.pub. So you basically have here private and a public key. And so if you just name your keys like that, then basically SSH will just look them up and you don't have to specify the -i option to kind of select the default key. And when you create the keys, you also kind of just can give it a passphrase. So as said, as always, there's a couple interesting options for those commands. Especially for the keygen, you can kind of select the algorithm. You can select how many bits you want to give the key. The more, the better, right? The more secure. You can give it a passphrase and you can save it into like some specific file, which will create like kind of the private key file and the public key file. So how does it work? Well, you would just run it, and then basically it prompts you to enter a passphrase. You need to just like enter it again to kind of confirm you didn't forget it already. And then it creates the 2 files and prints out like a fingerprint and like some random art to kind of see that like something cool random was like generated as a key. How that looks like is like this. So you have like kind of your large private key file, and then you have a public key file. In the public key file, you basically see that first there's standing like SSH -RSA. So because we basically want to upload the public key to the remote server, it kind of has to agree with the client which protocol to use. So that's why there's that kind of SSH -RSA at the beginning. And then we have like our public key, which is like all this bits and bytes coming after it. And then at the end, we have like tuxed server. And so that's basically identifying the user and like the host from which like the requests are coming.
What are these in? Because all those queues are not in hexadecimal.
Sorry, what?
What is the key coding in? Like, what is COL?
Oh, you mean like all these letters?
Yeah.
Well, that's just like kind of your key encoded using like, I think it's a base 64 encoding, but not 100% sure. But it's basically, I mean, what this means is basically it's just data which serves as the key.
It's supposed to be a number, right?
Yes, it's a number. It's just like bits in the end.
It's a number that's represented with all the letters in the alphabet.
Yes. So, I mean, it's like in the end, right, you represent some number and like how you encode it depends on you, right? You can use it as UTF-8, you can use base64, you can use any encoding you want.
So when you generate the public key, you have to like transfer it into the remote machine that you want
Yes.
to SSH into?
Yes.
So that lets you like that lets you SSH without using a password?
Yes. Yeah.
Oh, okay.
Is there a way you could like if you have a SSH machine and it has a log of like certain IP addresses that it could accept?
Mhm.
Do you kind of log in that way, or does your like your IP address always changes, so it's not going to work?
So you could do this. This is like host-based authentication. That's basically what rlogin did. But that's a bad idea because you could fake an IP address pretty easily. However, there's like ways to like host-based authentication, but it's in general not considered safe, so you just shouldn't do it. So basically, it's better to use always key pairs. Right, so yeah, second step is kind of we want to copy the SSH keys over to a machine. So we basically have to store our public key in the user where we want to log in .ssh authorized keys. And the easiest way is to just use like kind of the append for that. And there's also a command which kind of helps us to do all of that. But in the end, honestly, it's pretty easy to just copy it. So I would just like manually usually copy it over. And then finally, after we did all of this, we can log into a machine using our key files. And so this is kind of pretty cool. So let me just maybe quickly demonstrate how this works in real life. So I basically have like here my folder SSH, right? Already a couple files, but not much. And so first I want to kind of generate a key. So I want to use RSA. I want to use, let's say, 2048 bits for that. And I want to just call it like tux key or something like that. And I want to store it in this folder. So I just do it like this. So now it asks me for a passphrase. Just like in order to not waste too much time, I'm not going to enter anything. So I'm just going to skip it using enter. But you should like kind of put one that's like your secret. And so now it kind of generated the key. So if I kind of look into my folder, I have now in SSH kind of my private key, which is just like the tux key file. And then I have like my public key, which is like this file. And so as a next step, I have to copy this over to the remote host where I want to log in. So what I do is, again, I just go to the remote host, so I SSH in there. So I already gave like the hostname shortcut CS6 server, so I'm a little quicker on that. Then I have to type my password. And so then I'm here. Now I have to put this into authorized keys, so I basically go in SSH authorized keys. Then I just have to kind of copy it in here. I save it. Then I exit the whole thing. And now what I can do is I can just use my private key to log in there using just like key pair-based authentication. So if I do now this and just like use that syntax, then I'm already logged into my computer and I don't have to type any password, and it does like all the whole thing like safely in a cryptographic way. Yes.
So in this case, because you gave them the public key, and then when you enter, you give the private key. They only know that you're authenticated because they manipulate the public and the private to do something, right?
Yes. So the whole protocol is actually So the whole protocol is actually quite complicated, and it's definitely a good read for like a lonely evening. But like how it works under the hood is basically first there's like some initial connection established, then like some secret is shared, then you basically want to authenticate each of the hosts to be sure that they're the real ones. Then you kind of do the whole public key cryptography, which like has like the double key exchanges and so on. And then after that, at some point you end up with like a shared secret. And this shared secret is then used to encrypt all your data that you stream between those two devices. So for this reason, kind of what the SSH does is creates a safe tunnel from like your machine to the other machine, and like pretty much nobody is able to break that unless they have a good government contract. Yeah.
The first time you did this, you had to like manually go to the server machine and put the key.
Yes, exactly. And so usually that's like when you start up a server or like want to get access somewhere, usually either drop them a key so they add you for that reason, or you have to do like an initial login and like put the keys there. And then you can also like do something like first you enable password as authentication and then you disable it to kind of only have it then key based there. Yeah.
So let's say there are two users, one is authenticated and one is not.
Yeah.
But they both have a private key. So theoretically, and then there's only one private key in let's say the server, right? And in this case, if they both give in their private key, how would the server know that this is the authenticated one, this is not? Because is it because they would compare, because they only have the private key, they don't know the private, they have the public and not the private, and so it's kind of hard to.
Yeah. So how it works is, so basically you have your key pair, right? And if you want to authenticate a user to log in into this machine, you put her public key into authorized keys. And so that means that basically they can then use their private key for establishing a connection and so on.
Based on that, dude, as a server one, I guess I'm trying to understand, would they try to like combine it? Would they like calculate something, you know, to determine that that's the private key that works compared to another user?
Yes, it goes a little back and forth, which is like all details about the protocol. Yeah, so I mean, I can give you a link to the document if you're interested to read up on it. And usually also like a good cryptography class should handle that. Kind of went over like what the details are. Right, cool. So that means we have now a very nice way to log in remotely, and we can do a lot more cool things, which is we can kind of lessen the burden of having to type so much always on like login scheme. And so how this works is we can basically store a couple configuration parameters in like .ssh config, where we kind of just specify our host, what it kind of resolves to, which user we want to use to log in, and which private key file to use. And so if we do that, then let's hope that this is all stored still. Then if I go to SSH config, yeah, it's still all stored. I can do something very, very cool, which is just, I can just type SSH and then CS6 demo, and then I'm directly logged in. So I didn't have to specify any parameters to kind of log in, didn't have to type any passwords or so on, and I'm still kind of logging in fully encrypted and safely over the internet using just like my machine as a terminal or client. And so for that reason, I kind of mentioned in the lecture, because this really, really makes your life easier, and you don't have to define aliases or stuff like that. You just have to configure SSH properly to kind of work with it in a very, very smooth way. There's also like kind of a couple other details regarding SSH, which is like when you first connect to a new server, you want to be sure that the identity of the server is like kind of the real server, so it's not faking to be someone else. And so therefore it usually asks you to accept a server's fingerprint, which is just like kind of a hash over like some, again, public key cryptography to authenticate this server. And so if you work on your shell and you happen to come across a complaint about, hey, there was a mismatch of the fingerprint, then I just want to kind of tell you what this means, and that is like 3 scenarios could basically have happened then, and why you should be kind of a little wary when this happens. That is like, first, the system could just be like upgraded, which means there will be a new key which kind of serves to generate the fingerprint and establish an identity. The second is like the host name or IP changed, which means someone new kind of entered under this tag, and now you're connecting to this person. And the third one is what kind of the whole protocol tries to protect against is someone just went into the middle and tried to do a malicious man-in-the-middle attack. Hence, if there is like kind of a warning about, yeah, there's a fingerprint mismatch, this means that one of these 3 scenarios is true. So before you accept to kind of replace the fingerprint in your configuration files, just kind of make sure nothing weird is going on. Right, there's like then the 2 options to kind of remove a host name from known hosts. So if you kind of want to update it, that's kind of the way to do it. There's another one where you can add explicitly a fingerprint using SSH keyscan, which is handy if you want to remotely install stuff. And so, yeah, just as a quick summary, we have kind of all these different configuration files which you can use to tune SSH to our needs. You can use -v to see what's happening under the hood. And so I just want to kind of give, before we end the lecture, 2 more cool applications what you can do with SSH. And so far we just used it to basically log in. However, we can also use it to run any arbitrary command on the remote server. So how this works is basically you just do SSH, then all your login information, then you just specify the command you want to run. So for example, if I just want to know what kind of files Tux has on the remote machine, I can do just something like SSH CS6 demo and then list home Tux. And so this uses now my key pairs and so on, and I just have like here printed out what the files there are. And I mean, that can be used to install like software and stuff just like quickly from one local script, for example, which comes in quite handy if you want to automatically set up a server quickly. Another cool application is, so Linux has actually one way or like one possibility to have a graphical user interface. And you can actually forward this graphical user interface over SSH by just using X server forwarding, which is the option -X. And so why is this cool? Well, let's check it out. So basically what we can do is we can go here and let's say, because I still have to do research, I want to read like some document, but I am somewhere at the world and I don't have access to like Ethereum and so on, so I'm protected behind some firewalls and so on. So what I can do is I can just use SSH and port forwarding and start Firefox with the library.brown.edu website. I have to accept the fingerprint, so that's like kind of just to be sure that this is like the real ssh.cs.brown.edu. Then it takes a while. I have to type in my password. All right, password typed in. Now slowly a process is starting, which is like this X-quartz, which basically displays my graphical user interface. It takes a while because it ships now my whole graphical user interface from the Brown server down to my machine. And so I hope this will kind of not take too long, but usually it should appear after a while. Yeah, there we go. So Firefox just started on the remote machine. I'm shipping the whole program over to my local machine. Then as you see, it's pretty slow because it ships all the information, all the elements, and then it should load the library.brown.edu website. So that's a cool way if you want to just use programs on the department machine via SSH on your own machine. Yeah.
So let's say I wanted to set up my own kind of like SSH. Like if I wanted to SSH to like this computer, for example.
Yes.
Does he need to download something in order for me to do that -X command?
So he should have a Linux machine, and if it's a Mac, you just need X-quartz. Then on this computer SSHD, so the SSH server must be running, so you just download Open SSH server, you install it, make all the ports open, so your firewall doesn't block the ports, then you should ship your public key to him, and then you can do that, yes. And then you can for example, play some video game or so, but it will be very, very slow, so I wouldn't recommend it, but that's how it works. And yeah, so here we have the website, right, and we can just use it, whatever, we can search some papers or so, like SSH if we want to have the original paper, and yeah, it works. So that's like one cool way to kind of work remotely. Good. Yeah, there's like kind of two more commands. I don't want to go too much into details, so there's secure copy, which was already mentioned on Piazza, so basically you can use that to copy files, and it works under the hood just using SSH. And so if you configured your SSH, you don't have to type the parameters for STP. You can just use it directly to copy files from remote to your local host. There's a couple examples, right? You can copy a local file to your remote host, vice versa, and you can also copy like files from two remote hosts to each other. There are a couple problems. It's slow. It's just a plain copy, so that means it always will read-write all files and encrypt them via SSH. So at some point you maybe want to swap out the encryption algorithm to just have a faster one if you copy a lot of fast files. And there are some more issues in the case that it can't resume copying, so it will always start like from scratch. It doesn't show progress and so on. But luckily, as always under Unix, is there another tool? Oh yes, there is. And that is called rsync, which is short for remote sync. And you can see like remote sync as kind of a beefed up version of SCP, which gives you all sorts of cool features, like showing a progress bar. You can include, exclude files. You can kind of select what files to run. And what's also very useful is you can basically perform a try run before you overwrite any directories remotely or like locally. Speaking of that, we're at the end of this lecture. There is a lab this evening, which I highly recommend to visit, because it's, again, about all sorts of cool terminal tricks and how to use Tmux, which is a terminal multiplexer. Thanks.
201?
Sorry?
Labs in 201, right?
Yes. Right. Thanks a lot, and see you all next Thursday. This Thursday.
About a